The first method for the open methods is called simple fixed point iteration method. It is the simplest method, and it's also called fixed point because there is 1 point estimation, and that's why it's also called 1 point iteration or successive substitution. What we do in this is that we have a function like this, f x equals 0. We try to rearrange it so that x is on the left hand side of the equation. If that's possible, then we can use this fixed point iteration. So simply we are writing that x should be on the left hand side. So I'm not going to write f, but because we are isolating x, it will be another function now. That's why I write it as gx. So we will write this fx as this function. We can do this by either algebraic manipulations or simply adding x to the both sides. By algebraic manipulations, if it is not possible, or then we can use also adding x on both sides or to both sides. You can see an example here. For instance, let's say we have x squared minus 2x plus 3 equals 0. We just simply want to move 1x to one side, isolate 1x, and keep the rest on the other side. We can just do this. X is equivalent to x squared plus 3 divided by 2. What we did is simply we actually had this on the we actually kept this here, move this here, and x squared plus 3 and divide by 2 gives us x, like this. So on the other side there can be x's as well, but on one side there should be one x only. That's why, so this can be used for any functions as well. We don't need to isolate all the x's to one side. Another example, for instance, what if we have sinusoidal x is 0? In that case, we are not able to isolate x, but what we can do is just add x to both sides. X is equivalent to sin x plus x. So both sides, adding x to both sides. This is an example to that. And for algebraic manipulations, this is the example. So the idea of this is that now this provides a formula with x to assign a new value for x as a function of an old value of x, let's say. So if we have an initial guess at the root xi, then we can use this xgx simply to compute a new estimate, xi plus 1, as expressed by the iterative formula. That's why when we have this, like these examples, when we have these are gx values, then the next iteration becomes xi plus 1 is equivalent to gxi. And we can also use the error again as absolute error, which is between xi plus 1 minus xi divided by xi plus 1 times 100%. So these are the simplest formulations of fixed point iteration method. And we see a linear convergence in the fixed point iteration method because we simply add one x as a linear increment, let's say. And the error is approximately halved or reduced less than half at each iteration. So this error should be half or less than half of the previous error, let's say, for each iteration. We are going to have an example for simple fixed point iteration method, example 6.1, and our function is this, the exponential minus x. And the true root is given here, so we want to compare our results with the true root. So to use simple fixed point iteration, we want to have something like xi plus 1 is equivalent to gxi. We want to have this form. For this one, simply we can isolate x here and have this by algebraic manipulations. Then we will have x equals exponential minus x. And if we think that it will be iterative, then xi plus 1 will be exponential minus xi. So simply what we do is the right side will be the ith iteration, and the left side where we isolated x will be the I plus 1 iteration. Just keep this in mind. So this is the formulation actually. So we will start from beginning. What we will do is, let's say I equals 1. Let's start with an initial estimate. This is just we just made this up. We say that okay, let's start with xi equals 0, x1. x1 is 0. In that scenario, xi plus 1, we will use this. It's important. That means x2. Actually, x2 is equivalent to I0, which is 1. Simply. Then we will continue. I equals 2. Now x2, and we found x2 as 1. That means x2 is 1. So we simply move this here. Then we continue with x3 is equivalent to exponential minus xi, means x2 is 1. So this is the exponential value. And exponential minus 1 is simply 0.367879. I will just use 6 significant digits. And I equals 3. Then x3 is this value, 0.367879. Then x4 is exponential minus 0.367879, which is 0.692201. Let's continue. I4, x4 is 0.692201. Then x5 is exponential minus 0.692201, and the result is 0.500473. Of course, we need to calculate the errors, by the way, and from here, in the first iteration, we don't have approximated error because we don't have a previous value. Then we can just say this 100 in the algorithm, for instance, but the true error can be calculated based on this. And the true error here is 100 because the estimation is 1, but it's about 0.5. We can say this is 100 as well, or actually this is not 100 exactly. If we calculate, it is simply 76.3%. For the second iteration, the approximation error reduced to, actually it's increasing, 171.8, because from 1 to 0.36 it's a big jump, and the true error is 76.3%, so it's decreasing. And for x3, epsilon a is, so it's a reduced error now, it's getting closer, and the true error is 35.1%. And for 4, epsilon a goes to 38.3, and epsilon t is 22.1%. As you can see, the error is reducing like less than half. So this is the expected. So roughly 0.5, 0.6 reduction compared to the previous one. Let's continue. I equals 5. So x5 is the previous value, 0.500473. Then x6 is exponential minus 0.500473, and the result is 0.606244, and the error is 17.4, and true error is 11.8. Let's make one more. 6. x6 is equivalent to 0.606244, this value. Then x6, I will just write the value now. I'm not going to continue writing all of these. The result is 0.545396. So you can see it's getting closer to the true value over here. Then the approximation error is 11.2, and the true error is 6.89. So we keep moving. I equals 7. x7 is equivalent to 0.545396. x7, then when we have the exponential negative this 0.5796112, then the approximate error, actually this is 11.2 and this is 17.4, 11.2, and epsilon t is 3.83. If it is I8, then x8 is 0.579612. x8 is equivalent to 0.560115. Again, the error is 5.9, and true error is 2.2. I equals 9. x8 0.560115. Then x9 0.571143, and approximation error is 3.48. You can see that the error is reducing slowly and slowly, but it's going somewhere. This was 0.2.2 and this is 1.24. So let's stop at I10 because the true error will be less than 0.1%. This is 9. This is 10. 0.57114. And x10 is equivalent to 0.564879, and the approximation error is, so I think we wrote these wrong, 8, 9, 10, 11. So 11th is this, and the approximation error is 1.93, and the true error is 0.3399. Sorry, not 399. But if you continue, you will see that 0.705.